So it's my pleasure to introduce Sandu Popescu from Bristol, which, among many other things, has a P in PR boxes named after him. And I think he's going to tell us something about
other things. Okay, well, thank you very much for inviting me here. So, I'm using the opportunity that you have these beautiful whiteboards and even blackboards on the other part, so that I can change my mind at the last moment what to talk about. So I saw that you had a lot of lessons about hidden variables and about non-locality and things like this. So I thought that perhaps the best thing would be not to talk about that. So I'm going to talk about something completely different. And so that would be about time flow in quantum mechanics. I already see some strange looks on your faces, which is much better than seeing them in the laptops. But here is the idea. By the way, I just love this room. It's so much harder to keep the laptop than in the amphitheater. So that's good. Yeah, time flow. By the way, as you probably all noticed, we are just getting older all the time. In fact, I do. And well, this is quite well known, unfortunately. One of the questions is, why is that so? And there are a couple of sort of very popular answers. One of them is to do with the increase of entropy. This is called the thermodynamic error of time, which essentially means that the universe is just getting more and more disorganized all the time. And if we try to put a little bit of order in one part, the rest becomes even worse. So this is the thermodynamic error of time. Then there is, of course, the cosmological error of time, saying that the universe started with a Big Bang, which is just expanding, and somehow time passes with the increase of the radius of the universe, and so on. And by the way, these two may be, in fact, quite related. But quantum mechanics apparently introduced a third possibility. Namely, as you know, whenever you perform a measurement, there is an irreversible process that takes place, the collapse of the wave function. Now, of course, I talk about the collapse of the wave function. You may not like it, you may prefer many words, whatever. For all practical purposes, everything is equivalent with a collapse. So I will stick with that for a moment. So that is an irreversible process. So here it's not a question of perhaps things are irreversible, like I was talking about the entropy, but there all the underlying laws of physics are reversible. So one really has to work very hard to get irreversibility out of reversible laws of classical mechanics. Here, you perform a measurement, boom, that's it. You destroyed the state. So people thought for a while that this will somehow introduce now a fundamental error of time in quantum mechanics. Well, in nature, so therefore you can see that. It turns out that that is not the case. And this is a long story that I will try to summarize a little bit here and see what other outcomes it had. Let me start by telling what is the situation in classical mechanics. See, in classical mechanics, suppose you have a particle and you know what happens with it at the time t0. You know the position x0 and the speed. And suppose that you fully know the dynamics. You know all the forces that act on this particle at all times. In that case, this is enough to find the word line of the particle. What will the particle do and what it did? So no measurement that I'm going to do in the future gives me any sort of new information. Because in principle I can compute from the values at t0 what the result of any measurement will be. Also, if somebody told me where was the particle some time ago, I don't care because I just can compute where it was before. Now quantum mechanics is completely different from that. Because suppose I know the state at the time t0. I fully know the quantum state. And suppose I completely know the evolution. So I know the Hamiltonian, I know everything. And suppose that at this moment I perform a measurement of an observable B that may have different eigenstates, B1, B2, Bn, with associated eigenvalues. I don't know what the result will be for this particular particle. Of course, I can compute the probability for different answers if I would repeat this measurement many times. But for this particular case, particle number 1, I don't know what the outcome will be. Therefore, when I arrive at T final, and I actually perform the measurement and I find the result, I find some new information about the particle. Something that I didn't know here. So, future gives me new information about it. The interesting question is how to make use of that new information. So generally what people say is the following. Look, suppose it so happened that you got B1, therefore at this moment the state collapsed, it is no longer psi, and if this was an ideal von Neumann measurement, from now on the state will become B1 and will evolve according to the Hamiltonian till another measurement will occur. And so on. Now the interesting thing then is that the result of this measurement doesn't have implication only to the future, but has also implication towards the past. That is, events that take place here are influenced both by the preparation at T0 and by this selection at T final. How can I see that? Well, let me have an ensemble of such particles, each of them that is prepared in the same state, psi, at the beginning. And on which I perform the measurement of operator B at the end. Now, on this one, suppose I obtain B1. On this one, I may obtain B1 again. On this, I may obtain B2. On this, I may obtain B7, and so on. So what you see here is that I have an initial ensemble of particles, and this ensemble can be split into sub-ensembles that are pre-selected and post-selected. So according to the outcome of the last measurement, for example, these two belong to an ensemble. This and some other particles, and this one here, may belong to another sub-ensemble, and so on. So now, if I perform measurements here, in the middle, the statistics of the measurements, say, in this sub-ensemble, and the other one there, may be different, and in general will be different, from the statistics of the measurements that appear on everything. Now, of course, you may say this is quite trivial, and we know this in with classical probabilities. If I have, for example, a box that contains 99 black balls and a white one, the probability to extract a white one is 1 in 100. But suppose I take a ball, I don't look at it. I put it in another box that contains only black balls. Then I extract a ball and I look. So suppose I see it is white. Now I ask, what was the probability that I took a white from the first one? Well, since there were no white balls in the second one, the only way I can get one is that I moved it from the first. So I modify my probability from the first box by an event that takes place in the future. Now, that of course is a triviality, and I don't want to enter into that triviality. Why is this conceptually different? Well, because in the classical case, the only problem was my personal lack of information. When I put my hand in, I didn't look, I didn't touch it properly. Have I done that? I could have already established that from the beginning. Here, what is fundamentally different is that at this time, there is absolutely no way to say what will happen. So, as an example, these things occur for, say, many times when you are talking about collisions. Say you have scattering, here you send particles towards the scattering center and then they go out. Now this is the classical image. In the quantum image you would send a plane wave towards the scattering and some circular wave will emerge. And now you may say, look, I'm interested in events in which I send a particle in this beam and it happened to end up in this detector. Well, and this is what you do. This is what people do at CERN. Otherwise, they will have an enormous number of events. So they just want to post-select the events that are interesting. But classically, there is nothing conceptually interesting there. Because you could have prepared more carefully this beam to know exactly that the particle started here, exactly the speed, and then you could know in which detector it will end. Okay? It may be impractical, but conceptually that is possible. Quantum mechanically, you prepare your plane wave, there is no further information about it. The fact that it arrived at this detector is something brand new. Okay, so if you think this way, this tells me that the future tells me a couple of things. The future allows me to refine my answer. Okay. Generally, you would prefer to work with the cleanest possible system that you can prepare. What we see here is that the cleanest thing I can prepare is to both pre-select and post-select. Or let me put it in a different way. Suppose that I do what people generally do in quantum mechanics, to start with a state psi and do measurements on it. I can always think that at the end I perform one more measurement of the observable B, and I look at the answers, and then I forget about it. The ensemble that is just pre-prepared is like pre- and post-selected ensemble when you already forget about what happened at the end. Okay? So it's clear that you lose information by not making the post-selection. You lose information, therefore you will not see interesting things that you may have seen if you would have looked in each sub-ensemble separately. Okay, what interesting things can I see? Well, let me first ask a naive question here. Okay, let me just for symmetry to call this state one of the eigenstates of B, let me call it phi, just to make it more symmetric. So this is one of the particular eigenstates. So suppose that the evolution is such that there is some evolution during this time, t0 and t final. And here I perform a measurement of an operator A with eigenstates A1 up to An. And I ask, what is the probability to get A1 equal A1, given that I start in the state psi, and given the fact that when I measure the operator B, I obtain the outcome corresponding to phi. What is this probability? Well, let's calculate it. I start with state psi. So first of all, the probability that I start with psi and I obtain the answer, well, let me put some AI just. I obtain the AI. That probability is psi. I propagate it in time from t0 to t, AI, and I take the absolute value square. That is the probability to start from here and obtain the answer that I'm interested in. Now the state collapse on AI. What is the probability then to obtain phi? Well, I have to start now with AI, continue and propagate from t to t final, and project it on the state phi. Well, this is not everything. This is the probability that starting with psi to get AI and then to get phi. But I want the conditional probability, given that I get phi at the end. Well, for that I have to normalize by the overall probability to get up phi, which is simply sum over j of this whole thing, UTF t, aj, u, t initial psi. It looks a bit horrendous, but okay, that's life. This is just a trivial conditional probability for this system. You already can see a couple of things. First of all, you see that this formula is symmetric between past and future. And I may come back to this. But you see something interesting. The standard way of computing it, as I described, I start with psi and I evolve it in time from t0 to t. I collapse it on AI, then I take AI, I propagate it in time up to t final, I collapse it, and I take the scalar product to phi. If I want to do that, I have to work quite hard, because I want to find also this normalization factor. And when I want to compute this normalization factor, I have to take all the different j's here. So here I propagate psi to the intermediate time. I take the scalar product with aj. But here, I have to take all different aj's, solve a differential equation for each of them, propagate up to t phi. A lot of complications. But I see that there is a simpler way to do the computation. I will apply the time evolution operator to the final state. Now there is just one state that I propagate. I still have to do the scalar products with aj that I have to do in any case. But there is just one single time evolution that I take into account. Okay? So here's the image. As far as this intermediate time t is concerned, I can propagate psi and I can propagate phi backwards. And out of those two things, I can deduce the physics at time t. Okay? Now, generally, when you see an important simplification in your way of calculating something, that is a signature that you are on the good track. So the question is to try and get something more. Up to this point, it's nice, it's interesting, but perhaps it's not really so exciting. These are, after all, just conditional probabilities. So to see if we can get something interesting, it's always good to start with some particular examples and see what we can do. So here it's an example. My example is a qubit, or for physicists, like a spin-half particle. And suppose I start with this prepared such that sigma z equal plus 1. Sigma z or z, and I don't know exactly how it was described, is a spin-half particle polarized up in the direction z. And to make it simple, I take the Hamiltonian equals 0, so nothing happens to this particle. At a later time, I'm going to measure sigma x, or the x of it. The eigenvalues of the eigenstate of sigma x are, of course, superposition of eigenstates of sigma z plus minus. So in general, here, I can obtain either sigma x equal plus 1 or sigma x equal minus 1. By the way, are you familiar with eigenstates and operators and sigma x as a function? So suppose I'm just looking at a pre- and post-selected ensemble in which the answer to this final measurement is plus 1. Whenever I get minus 1, I disregard it. I don't care about it. But let me ask the following. Suppose I measure here sigma z. What will be the answer? Sorry? Plus 1. With what probability? With 7, because that's how I treat it. Let me try to use a little bit the board. Suppose now that instead of sigma z, I measure sigma x. Here. What am I going to obtain? Plus 1. With what probability? 7. So I already find an ensemble of quantum particles that two non-commuting observables, sigma x and sigma z, can give well-defined answers. This is something that I cannot do at one time. Here it's an ensemble that at this intermediate time t, between t0 and t final, both sigma x and sigma z are perfectly well-defined. Okay? This is something new. Right. Let me go forward and ask something more interesting here. Suppose I measure another operator. This is the spin in 45-degree direction that is defined to be sigma x plus sigma z over square root as operator. You can check this is an operator that has two possible eigenstates and two eigenvalues, and the eigenvalues are plus and minus 1. It is another of a combination of Pauli operators with the correct normalization so that the eigenvalues are plus or minus 1. So I measure this thing. What am I going to get? Well, let me tell you what I'm going to get. I we just saw that at this intermediate time, both sigma x and sigma z are perfectly well defined, and they are equal to 1. So sigma x is 1, sigma z is 1, over square root of 2. This is what I'm going to get. Sorry? Am I doing something wrong?
Yes, you did.
What? Come on, speak up. What is wrong?
You're not following the same set of rules, huh? You should have taken the eigenspace and then projected. You could never get anything out of one. If you did follow the rules.
That's absolutely perfect. You see, this is the trick. You present people the rules, and then you do something different. They will never believe that you are not doing the correct thing. Well, apart from some pedantic guys that don't care about the rules, but okay, you tend to. I showed you what to do, and I didn't do it. I should have, this is sigma x plus 1, this is identity, and then I have to look what are the eigenstates of the sigma in 45 degree direction, do, and I will find that I can obtain here either plus 1 or minus 1 with relevant probabilities from them. So that is a lesson for you. Never be tricked by people who tell you first the rules and then do other things.
I don't understand how you can measure the intermediate state after the final state.
Oh, no. No, I measure it before. I measure it here. Then later, you see, this I do Monday. This I do Tuesday. This I do Wednesday. Wednesday, I may obtain plus 1 or minus 1. If I got minus 1, I throw this experiment out. And I start again next week. Monday, Tuesday, Wednesday. I got plus 1. I said, fine. And then I want to go back and see what was the experiment on Tuesday, given the fact that Wednesday I obtained plus 1.
Doesn't sigma 45 not have a definite value for sigma z is not an eigenstate?
Oh, sorry.
Eigenstate?
Sorry, I just showed you that if I measure sigma x here, I obtain plus 1. I measure sigma z, I obtain plus 1. And you all agreed. I didn't tell you it's plus 1. You told me. So I just put them there.
Well, that's simpler, but addition doesn't have to work with that.
Here's lesson number 2. There is a good reason not to want to trick the rules. You see, that's why people do it. Not because they don't want the rules, but sometimes if you want to break the rules, and you break the rules in a good way, you may find something interesting. So here it is. I should have done exactly what Reinhardt told you. Follow the rules, get those results. But this is so nice. It's really so nice. You laugh. But when you find something nice, you really want to have it true. And in fact, when it is nice, it may have a chance of being true. So, so the idea is, perhaps this is the correct answer. But perhaps the question was slightly wrong. So let me try to see why don't I get this answer and what to do to get it. Okay? Right. Let me go back. Let's try to do a more complicated thing. Suppose I measure sigma z here, and I measure sigma x afterwards. What am I going to get? Plus 1 plus 1. Sure? With circle. Good. Let me play the same game again. Sigma z equal plus 1. Sigma x equals plus 1. Suppose I measure sigma x, sigma z. What am I going to get? Sorry? The same. Okay. That's
Sigma x doesn't have to be the same because we have regeneration by doing the double sigma z.
so I can get anything. Yeah. With equal probability. So that's the point. You see, my claim was that at this intermediate time, both sigma x and sigma z are well defined. But they are well defined as long as I measure them separately. I can either measure sigma x or sigma z. But if I attempt to really check that fact by measuring sigma z and sigma x, I see that these two things do not commute. So since they do not commute in time, I cannot even measure them simultaneously, which is the measurement of sigma in 45 degree direction. So this is the problem. They don't commute, and I was wrong. Well, just to make things sure, this is not that I was wrong. This is Yakira Haronov who started the thing in their knowledge. So he was wrong. But he was not silly.
But don't you be able, you don't have to measure them simultaneously like an experiment, just rotate your stern door-like apparatus.
That I can do. But this is formally exactly the same thing, and I can do by measuring them simultaneously. And there is where the problem arises. But let me continue to tell the story. So he was wrong, but he was not completely silly. Because once you realize that this is this lack of commutativity, now you start having a glimpse of how you can get the result that you want. Okay, let's do an experiment. Do you see this marker? Is it still here? So you measured its position, but you didn't give it an infinite Kitty momentum. You know, delta x, delta p. Okay, so why it is still here? Okay. Well, it's here because I didn't measure x with absolute precision. So there is a slight imprecision in measuring x, which allowed me to, in fact, have a control on the disturbance of the non-commuting variable. So the lesson is you can always limit the disturbance to one variable by paying the penalty that you don't measure another precisely. So let me just, because we are talking about spins here, I will never need these goods again. Remember, they are here, but I will try to ignore them and sidestep them. So here's how you can measure spins if you have many. You know, let me take a ferromagnet. A piece of magnet like one that you probably used to play when you were kids. Hopefully you still play with them. Now, how do I measure the magnetic field? Well, it's pretty simple. I take, say, a piece of iron, and if I want to make a measurement, I connect it to a spring, and I see how much this moves, and from the movement, I infer what is the magnetic field here. But I can also put a piece of iron like this, or I can put it like that. Now, when I put a piece of iron with a spring in this direction, I don't destroy the magnet. So it means I do not perform a measurement of sigma x that is completely disrupting the sigma z. Okay? Because this is what measures sigma x. Sigma x and sigma z and sigma 45 degree, they all commute. How is that? Well, I perform some disruption here, but not very big. And I measure the field pretty well, but not absolutely. In fact, if you would actually compute what you're doing in such a measurement, you have a large number of spins n, and you measure them with a precision delta n that is more or less like square root of n, which is a very good precision when the number is n. And you can arrange the measurement such that you don't disturb too much. That is probably something like 1 over n out of the total spins are disrupted. That a fraction of 1 over n is disrupted. So let's come here. back to our story. Suppose that I start not with a single spin, but I start with lots of spin. And all of them are up Z. And I finish that they are all of them up X at the final measure. And these are very good, these are ideal measurements, precise measurements. And suppose now that I measure sigma Z, but this is a macroscopic measurement of sigma Z. Okay? One like this that measures sigma Z with a precision of square root of n, but barely disturbs the state. What am I going to get here? Well, I will get n plus minus square root of n. Right. What am I going to get here? Well, this is the information coming from the future. Or in another way, in order for this to be consistent with that, I will get n Now what happens here? First I measure sigma x, then I measure sigma z. And here I start with f. And here I get f. You see, this measurement of sigma x doesn't disrupt the state. So the information from here just continues, slightly disrupted. So here I must get n. And again, this one doesn't do anything to the state coming. So in order to correspond to the final, or if you wish to get this information back, you have to get that back. Sigma z equal n, sigma x equal n, sigma 45 degree, sigma x. What am I going to get now? Now this is a much more complicated observer, but yes, they have all these 2n plus 1 eigenvalues. Well, here's a claim. Now they commute within square root of n. So what I will get here is n plus n over root 2 square root of n, which equals root 2n enormously much larger than n, which is the maximum possible eigenvalue for that observer. And square root of n, the errors, if I take this enormously large, this is insignificant.
And then you actually done an experiment and obtained the
Yeah.
results. Like that's awesome.
Yes. Some people did. Not exactly with the spins, but in other systems. So they did it with light, with photons, and with different things. And then at the moment, this method is at the basis of one of the most powerful amplification methods. Because you may view this as an amplification. You amplify the values of the spins, and if you would put the spins in a magnetic field, it's like having a larger magnet to sample the field. So, do you want me to prove this? Here I just claimed it. Want me to? No, I don't want to do that. And I tell you why not. Because I would like you to try to do it. It's complicated. And here it is what is interesting. What I have to do in order to obtain this, remember I claim that I'm doing now a measurement that is not completely disturbing by the way, I start with the fact I want a measurement that is not disturbing, and there is a penalty that it is not absolutely precise. And here it was, with all the spins here, and I had a piece of magnet, and this one moves, and so on. So you have to model how this thing works. And let me tell you how it works. Let me just look here. You see, this is a piece of iron on a spring, and when there is a force, this is pulled. So this originally has a wave packet. Yes, it's the ground state of a harmonic oscillator, and will be pulled. Now, it depends how much it is pulled. Whenever this one, I told you, that has an error plus minus square root of n. So it means that if I would flip only of order square root of n of the spins, it will quite overlap with that thing. It will come into a completely orthogonal or almost orthogonal situation only if I flip more than square root of n. So the measuring device will be shifted by different values according to the spins here. Now in the z direction, of course, they are all z, but in 45-degree direction, I can decompose now this along 45 degree. So there will be lots of terms in the superposition, lots of different ways in which the measuring device is pulled. Each different location of the measuring device is entangled with another eigenstate. Here I'm doing what Reinhardt told, to look at the eigenstates. So I'm looking at the eigenstates, and they will get entangled with pulling this piece of iron. But then I destroy the entanglement because I select this. So now there will be an interference, complicated interference. And the result of that interference in the measuring device, so if I look here at sigma 45, that can have values between 0 and minus n, and the most it can give is plus n. But out of interfering all kind of things here with different magnitudes, and by the way, some of them will have negative values, all these will give destructive interference, and you'll get out of the tails of all these Gaussians, you will get a little peak there, out of the blue, at square root of 2 times n. So you go and you model the measuring device, and you work out your quantum mechanics, and you will find a result that I can predict for you here, just by thinking of these two-way function, taking it seriously the fact that I have information coming from the past and from the future towards this point, and calculate the value. It is instructive to do that because that is the standard view of working everything out in the normal way. And then you see how complicated it is. But it turns out to get this result. And it turns out to give this value no matter how you measure. That is important. So it is universal. As long as I perform the measurement in such a way to limit the disruption to the other state. So that the information coming from the future and from the past can propagate the intermediate time. When here I just look at strong measurements, the information was disrupted. Okay. What is the general idea? If I perform a measurement of an observable A, here, I measure an observable A, I start with the state psi. I perform here a measurement of B, and I select only the events when the state is phi. And this measurement is what I will call weak. Doesn't have to be very weak. Weak, I mean a sort of macroscopic measurement like the one I described. That is precise but not absolutely precise. This is the value that will be indicated by the pointer, phi a psi divided by phi psi. You can see that this is a particular solution for that. This value can be larger than the largest eigenvalue of A due to the normalization coefficient. This value can also be complex. How am I going to see that there is a complex value? Well, remember, this is what the pointer of your measuring device indicates. So you'll have a wave function for the pointer of the measuring device, and the claim is that the measuring device is shifted to indicate a value that is complex. So you put a complex number in your wave function for your measuring device, and that will just result in a phase for the thing. So a phase in the state, in the Q representation, where Q is the location of the pointer, which is the same as to say that in the conjugate representation of the pointer, you'll see a kick. The pointer doesn't move. Stay where it stays if the value is purely imaginary, but just gets a velocity. Let me give you an example. Here is something that probably you learned in the first course of quantum mechanics. And if you didn't, you should have. It's a square potential well. And suppose I have a particle in this potential well that has energy smaller than, suppose here potential is 0, 0, and here V0, and I have E total that is smaller than V0. So classically I have a particle that goes back and forth here and it cannot escape. Doesn't have enough energy to fly down. Quantum mechanically, suppose you have, I start with this state, E total, that is a bound state in this potential well. And as you know, there may be tunneling. There exists some, that is the wave function, is not 0 outside the potential well. Which means that if I come and measure where the particle is, I have some probability of finding the particle here outside the potential well. Now, you know classically that cannot be the case, because then the particle will have, what will it have? Let's see. E total is E kinetic plus the potential. So if I find the particle here, then the potential is V0, so E kinetic would be E total minus V0 smaller than 0, but I know that E kinetic is P square over 2m, which by definition is positive. So the particle, if I find it here, will need to have negative kinetic energy. Classical. Quantum mechanically, all the textbooks, in fact, these are the older textbooks, when people were still worried whether quantum mechanics is correct or not, and they try to see how it works and try to explain. More modern ones ignore this completely. So what were they doing? They say, be careful. This is the way in which quantum mechanics works. Kinetic energy and total energy do not commute. Yes, kinetic energy is essentially P, but this one is P, so E total is P squared over 2m plus some potential V of x, and it's clear that E total doesn't commute with E kinetic. And also E kinetic doesn't commute with a position. So, you started with a state of given total energy, and then you measure the position. And you find a particle here. But because you measure the position, you modify the state. So by now, you will have a wave packet that is localized here. And if you look what is the kinetic energy in this modified wave packet, you find out that it's big. And in fact, it's bigger than V0. So now, legitimately, the particle could be found there. So this is a beautiful way in which quantum mechanics works due to non-commutativity. This is what all those good old books were telling you. It's true. It's absolutely true. But misses the point. And the point is the following. Let me look at a different experiment. Or let me look at this experiment in another way. Suppose I measure, the way I explained there was I start with a state of total energy, I measure the position, and then I measure kinetic energy, and I ask what is the kinetic energy. What I want to do something different. I want to make sure that I know both the position and the total energy. So I start with a state of E total. I measure the position. And here, in the intermediate time, I measure kinetic energy. And suppose I find a position x equal x0, that is here. I find this position x0. And I ask, what is the kinetic energy here? Well, if I measure the kinetic energy precisely, I will obtain a positive value. By definition, this operator has only positive values. So it can only give me a positive value. But you see, when I measure the kinetic energy doesn't commute with the total energy and doesn't commute with a position, therefore will disrupt the position. So suppose the particle started here, will be thrown out. And in fact, a precise measurement, an ideal measurement of kinetic energy, may take the particle and throw it up to infinity. But suppose I make a measurement that is not absolutely disruptive. I make a measurement of kinetic energy that may disrupt the position. So in fact, I measure P, say, but up to some delta P, therefore delta X will be like 1 over delta P. But since this is not 0, then this is not infinite. So suppose I can only throw my particle from the well up to there. And now I take my position x0 to be much further, here, x0. Such as I cannot throw it up to there. Okay? It's a combined view, this, yes, this is potential and this is space, whatever. So suppose I select particles much further than they can be thrown out of the potential well. So then I can say, look, that means that during this whole time, these were genuine tunneling particles. They both had E total fixed, and by the way, smaller than V0, and they were out. Therefore, the kinetic energy should be negative, and it should be E total minus V0 smaller than 0. And that's what my pointer shows. You can do the calculation, and you'll see that that is what happens. And how it happens? Well, let me go perhaps here. How will it show? Well, it will show, like in all the others, namely, if I perform a perfect, so this is the probability for E kinetic, and this is E kinetic, can only be positive. But my measuring device is slightly wrong, and sometimes gives me also negative values by mistake. And it so happens that in all the cases when later I get x0, which are pretty few, because if I go far apart, you know, it's again, the more precise I make the measurement, the smaller the errors, but the further I have to go. And I will find, if you do a histogram, you just collect these facts. You know, this you may imagine is the histogram of all the measurements that you do by measuring, preparing Monday, measuring Tuesday, looking Wednesday, and throwing away the events that you don't like. Namely, events in which x is smaller. All the events when you find a particle out will be here in the negative domain. I started by promising to talk about time, getting older. Perhaps you thought I'm not going to get older during this hour. I did get. The hour has passed. That's it. Thank you.
Momentous, so moment is you imaginary, so the square is negative. That's a standard explanation.
That is a wonderful mathematical explanation for what? I'm talking about
the fact that kinetic energy is smaller than zero.
Yeah. That doesn't tell you anything. Here I'm talking about a real measurement. Going in the lab, I'm measuring, and my measuring device, which is a very good measuring device, shows me negative values. Now, no analytic continuation tells you that your measuring device actually shows you negative values.
Well, the exponentially decaying wave function is analytical continuation from the oscillating in the complex wave, right? That's one which we wrote.
Here I'm talking about the indication of the measuring device. The measuring device will show you a negative value. The pointer will move the other way around. That's what I'm talking. I'm talking about a real measurement in a real lab.
So you're taking, as you were showing there, so this is a very fuzzy distribution that you get for your measurement, right? And all these weak values always only refer to the mean of that distribution, but there's no way to get something like a genuine probability distribution for this negative kinetic energy. You just see this shift in the mean. Right? So it's not at all like a measurement of a real value quantity. So it's just.
I'm extremely puzzled, I must say, about what do you think reality is. I go in a lab, I do the measurement.
But I get numbers, and these numbers have a distribution.
Yes, and they will be negative. All the cases.
No, absolutely not.
All the cases in which later I find x0, they will be negative. That was my statement. And there will be, by the way, you see, if I would start this thing.
Okay, but this is a particular pointer model that you need to do that, right?
But that's how I started. I'm only looking at the measurements that gave me the particle there. For all those, I get this distribution, which is beautifully picked here, and is not fuzzy at all. In fact, I can make it as narrow as I want. And the more precise I make this measurement, the more beautifully narrow this will be. And by the way, if I would start, instead of this particular state, I will start with an eigenstate of kinetic energy, I will get exactly the same profile here. So I can make it as narrow as I want. Of course, then I have a penalty. This one will be smaller, so the whole peak will be smaller. Because I need that the disruption will be bigger, I need to go further. But there is nothing fuzzy whatsoever. It can be as narrow.
That, but I guess I'll have to do the computation then.
It will be as narrow as you want. Yes.
You were talking about an experiment where this.
Oh, well,
Could you give some reference?
I wish I could. I wasn't prepared to give you, but I can tell you. So the first experiment was probably, there are many consequences from this thing. One of them was to make time going backwards in a so-called time translation machine, because you can make time go slower at different rates by coupling it to a quantum degree of freedom. And although time only goes slower, here by post-selection I can do it to be negative, so really faster. So there was an experiment that actually mimicked that in NMR by Ernst, and I don't remember the third author, from ETH Zurich. Then there were experiments in quantum optics. The most recent ones are experiments by a group in Rochester that they found displacement. They were using the amplification part of this. So they were able to measure displacement of a mirror of the order of femtometers, that is smaller than a nucleus of an atom, using this amplification. And another experiment is a paper by the group of Paul Kuyat that appeared in Science 2 years ago, connected with the so-called quantum Hall effect for light, in which again, very small displacements. The position of the pointer was a beam of light that measured the displacement of another quantum variables. So that is a paper by the group of Paul Kuyat, Science, around 2 years ago, so I believe something like that. And probably you can work it out from there, or you can look in a number of my recent papers that have to do with multiple times where there is a whole list.
Yes.
So this result basically arises from the basic idea that you treat the measure on the same footing as the quantum system. They're both quantum objects which interact, rather than from old quantum mechanics where we treated an observer as something external to magic. That's the idea I got out of this talk.
Right. But yes, if you want technical, yes.
Because previously the observer had a privileged position, while in your interpretation the observer doesn't have a privileged position.
It's not a question of interpretation. The question is what will you actually see. So this is a good point, and in fact philosophically it is interesting. You see, when Bohr was talking about measuring something, he said, look, you have the quantum world and the classical world, and the measuring device just indicates the value that there is in the quantum system. If you work your quantum mechanics here, you really have now to say that there are two attitudes you can take. One is, in order to prove all this, I have to denounce that picture, to take my measuring device to make it quantum, to show what interference will be, and so on. By the way, this I can do because in many cases, a quantum measurement involves two steps. A step in which you have another quantum system that interacts with the one of interest, and then you amplify that quantum system. Like for example, in the case of a Stern-Gerlach measurement, where you measure the spin, you first put the spin into the transverse momentum, and then the particle comes there and you get amplified. But it is at this step, when the pointer is quantum, that you can work. But coming back to it, Suppose you do not have an intermediate step like this, and suppose you do find these measurements. If you believe, and this is the point, that this indeed means that this is true and that is true, then you don't care what the measuring device is. Measuring device can be classical, because it reads a value that is there and belongs to the quantum system. It's not an interference in the measuring device. And that is important, since that interference in the measuring device is universal. That is a property of the quantum system.